So are there any questions about the homework assignment? Anything about the, any questions about the resolution homework assignment? No? No questions about that? What homework assignment? I think it's due on Wednesday because I postponed the homework assignment from last week. So that's why it is now due on Wednesday. Yes?
So if you don't have it resolved to anything in a resolution, does that mean it's false?
No. Okay. So you have to be more specific.
So after you do the negation and you end it with the function before, and then you don't resolve it to get it like all the way to get a 1, you still left with something.
No, you're not looking for a 1. You're not looking for a 1.
For a 0, yes.
You want to resolve the whole thing to a 0. So the question is, if you don't resolve the whole thing to a 0, what are you going to do? Right? You know, there are no further resolution that can add any new unique terms to the conjunction. Then the question is, what are you going to do? Well, if you go back to the module, remember in the module I have one example like that. In fact, it's the first one. So what was the conclusion when you cannot resolve any further?
It's not true that it's not a theorem.
It is not a theorem. That's right. It doesn't mean the expression is false. It doesn't mean the proposed theorem as a statement is false. It simply means it does not follow whatever is true to begin with. So there's a major difference between those two. If it follows, it means, you know, if all of those things that you're told to be true are in fact true, then this thing, your proposed theorem, also has to be true. If it doesn't follow, it can still be true, but it would not be because of everything else being true, because of the things that you are known to be true, but it is true for some other, it can be true for other reasons. Is that explaining what it is? Okay. Okay. I can give you a very quick example. I can just do it on the whiteboard because it's not really important to the class. So if I say x equals y, that is true. I assert that x equals y is true. So now I ask you, does w equal to z? In other words, I'm asking, is there an implication here? Does x equals y implies w equals z? Now obviously the answer is no, right? Because, you know, if I tell you ahead of time that all of these are independent variables, then x equals y does not guarantee that w would equal to z. Does it mean that w equals z is false for every single way to choose w and z? No, you can still choose plenty of, you know, pairs of w and z where they are the same. It just means that x equals y, it's not sufficient to state that w equals z is true. So it's the same thing with what we are doing. If your resolution step can get to a point where you're stuck, okay, you can no longer use resolution to produce any new terms in the conjunction. It's the same scenario like this one. Okay, w equals z is not a theorem because of x equals y. Does it mean that it's not possible to get, you know, w equals z to be true? No, it simply means it does not follow. Is that okay? I mean, it's a very important concept that we need to understand of, you know, what it means when we have something that is not a theorem. It doesn't mean that statement is false all the time. It simply means that it's not a consequence of things that you're given with. Is that okay? All right.
Thank you.
Yes, sir.
So is resolution adding more terms or reducing, or you can do both things?
So what it does is it is giving you more expressions or more well-formed formulae that are also known to be true. So as you add more of those terms, hopefully one of the steps in resolution will give you a false. Then you can stop, because you simply cannot have 0 as a statement that is true. That by itself is a contradiction. Is that okay? Is it answering the question? So if you look at, I will get to that. So if you look at the well-formed formula space as a as your haystack, what you're doing is you have certain ones that are labeled red to begin with, okay? And what resolution is doing is not changing the ones that are already labeled red, but it is also adding other ones to be labeled red. So you want to keep labeling things to be red until you label 0 to be red. Then you say, oh, that's not possible. Okay, so the negation of the theorem is leading to a contradiction, and as a result, the theorem itself has to be true.
So it's like adding more terms in the CNF.
Yes, you are adding more disjunctive terms to the CNF.
Until I hit the false, and then the whole statement.
Until you get to one of two conclusions. You can no longer add any new unique terms, or you hit 0. Yep.
Yeah, my question is kind of like that. I was just wanting to clarify, when you do a resolution, you add the terms onto the CNF, right?
Yes.
Okay.
So whatever
No,
you
like
use.
erasing or anything.
Yeah. So that's why copy and paste works, and that's why, you know, if you do it on using the browser, the editor, built-in editor, that's going to be a lot more helpful than doing it on a piece of napkin, because otherwise you have to copy and paste it a lot. Are there any further questions about the resolution and how it relates to everything else that we have talked about in propositional logic? No questions? So we all good? Now I did finish grading exam 1 for this class. That took me a lot of time. You know, I have to take a nap, you know, after every 1 question and a half or so. It's just very draining to me. I can debug programs all day long, 12-hour continuous, and that doesn't drain me at all. But grading does. I don't know why. Some people are going like, well, grading, that's the most relaxing things you can ever do. Not to me. So anyway, I took the lowest scoring question out of the pool. So there are 6 questions to begin with. Whatever is the lowest scoring question is not going to be considered a part of your grade. In other words, I chose the 5 highest scoring questions and divided by, you know, the base points of only 5 questions. Yep, question?
Is it like the lowest scoring for the class or for each?
No, for each person. So it's fair to each person. So it can be different for each person. You know, some people may choose not to answer question number 1, so question number 1 is tossed out. Other people may choose not to answer question number 6, so question number 6 is tossed out. Okay, so so I don't think people can say it is unfair, because if I just choose, you know, one of the questions and say, okay, I'm going to throw this one out for the entire class, there may be people who is getting a perfect score on that question and go like, no, that's not fair. Yep, question?
I have a question. I got a notification saying that you changed like the weight of some assignments, like the kind of weight it has. So like it says like the regular assignments have 0% weight.
I'm moving categories. I'm moving everything into the homework category instead of having a homework and an assignment category. So I was just, that's only clerical stuff.
Alright, like that. Yeah, because I got an assignment. I'm like, okay, so those 3 assignments have no weight on my grade at all.
No, it's all clerical.
Alright, thanks.
So after I made that adjustment to all the grades and using my scheme of 62.5% is a B, more than half the class is getting A's and B's. I would say about close to 2/3.
Who's the other 1/3?
Hmm?
Now don't answer that.
I cannot remember.
Okay.
Yep, I'm pretty good at keeping secrets because I cannot remember any secrets. They can use a memory scanner on me and go like, really, that's blank. Okay, so let's move on and talk about the stuff that we talked about last time. So what I want you guys to do eventually, not right now, but eventually I want you to write a program that can generate all the outcomes from experiments. So I'll give you the parameters of an experiment, and then you guys will have to generate all the possible outcomes. So I'm just going to first talk about the concept first. So there's no coding involved at this point because I don't want to give you 2 assignments at the same time. So we'll wait until at least Wednesday to do this. But what I can do is to tell you that the focus are outcomes of an experiment. Okay, so now we need to look at the parameters of the experiment. There are basically a few, like 3 parameters. Okay, so we'll have 3 parameters. Parameter 1. Okay, parameter 1 is just going to be the number of trials. Okay, so number of trials, if you remember, a single trial is something that you can do that can give you, a number of possible outcomes. Tossing a coin is a single trial. You cannot divide it any further into smaller steps. So tossing a coin is a trial. Picking a number out of a whole basket of numbers, that's a trial. So each trial has its own outcomes. Like flipping a coin has 2 possible outcomes, head or tail. Picking a number out of a basket also has a number of outcomes depending on how many numbers are left in the basket. That would be the number of outcomes for that single trial. So, but in an experiment, you can have any number of trials. For instance, if I have a hat, okay, or a basket with student IDs of this entire class for a raffle, okay? So, and I can say, okay, I'm going to pick 5 people, okay, because I got 5 prizes. So now the question is, how many ways can I pick 5 people out of a class of, let's say, 38 students? That would be the number of possible outcomes for the entire experiment. Because for the first trial, I have 38 outcomes. For the second trial, I have 37 outcomes, and so on, because this is called without replacement, which means once I pick a particular outcome from a certain trial, all subsequent trials cannot have that single outcome anymore. Is that okay? All right, so that's parameter 1, which is the number of trials. Then parameter number 2 is really just, is it with or without replacement? Because if it is like with replacement, like flipping a coin, that means if I have a head in one trial, the next trial can also be a head. The trial can also have a head, and so on. So I'm not removing any possible outcomes for subsequent trials. Yes?
For parameter 1, in number of trials, are you considering it a set, whereas there's no particular order to it, or
no, it's just a number, like 5, 10, 2. The number of trials is just a number. It's just how many trials is considered the entire experiment.
Well, I mean, like, do you consider a unique outcome to be Jerry, Terry, and then Bob, and then Terry, Jerry, Bob? Like whether or not the
whether the order is important?
Yeah.
The order is important. Yep. So parameter 3 is going to specify number of outcomes of trial 0. In other words, how many outcomes do we start with in this case? Trial 0 is just another way to say the first trial, because we count from 0. Is that okay? All right. So depending on how you want to do it, I would use, so each possible outcome is a letter in the alphabet. So we can have up to 26 possible outcomes. So this just makes it easier for me to read the answer. Okay. So I'll give you an experiment. I'll give you the possible outcome in one particular experiment. So we'll just say that we have 3 trials. It is without replacement. So I'm going to specify here with replacement, we specify a 1. Without replacement, we use a 0 to represent that it is without replacement. So in this case, let's say we have 3 trials without replacement, and the possible outcomes for trial 0 is also 3. Okay? So what your program should give me would be ABC is the first possible outcome for the entire experiment. ACB would be the next one. BAC, BCA, and then CAB, and then CBA. So you should have 6 rows as the possible outcomes for the entire experiment. Is that okay? Are there any questions? Yes?
So for parameter 3, that's implicitly bounded by 26, so it can only go up to
When it
26.
is without replacement, correct.
Oh.
Oh, yes, it is always bound by 26. But if it is without replacement, then you also have to make sure that the number of trials does not exceed the number of possible outcomes for the first trial. Because otherwise you run out of things, so that would not be possible. So is that okay? Okay, give you another example. 2 trials with replacement, and let's say we have 3 things to choose from in the first trial. But because this is with replacement, so that means every single trial have exactly the same 3 possible outcomes. Is that okay? So in this case, we have A, because it is with replacements, so 2 trials can have exactly the same outcome. AB, AC, BA, BB, BC, CA, CB, CC. That would be the actual list of all possible outcomes when you have an experiment where you have 2 trials with replacement, and there are 3 possible outcomes for the first trial. Is that making any sense? Okay. So that's going to be something that I want you guys to work on as the next homework assignment. It is a coding homework. I understand that many of you know like a gazillion programming languages, but since I only know a limited number, so you have to do this in C or C++, anything that G++ can compile. Okay? And Java is not one of those options. Yep.
So for the code outcome, you just want us to make a list of possible.
Correct. So I'll give you more information on Wednesday. I'll give you a snippet of code to begin with. In other words, I will show you how these 3 parameters are passed. I'm going to use argc and argv, the count of arguments and also the argument list in C and C++ to pass it in. So this way you can run your program with those parameters specified on the same line to specify, what the parameters are for that particular run. Yep. As long as the source code is compilable in G++. So the bottom line is, can I compile it using G++? Yep. So for those of you who are used to C#, you can do it in C#, but you have to make sure that the code is compilable in G++.
Right down.
Does Python sounds like C++? It's a question. I didn't say anything. I was only asking a question.
It's based on a C++ language.
If it compiles in G++, fine.
But it's probably not.
I don't know. It is unlikely because the way they do scoping is different. If you can find a translator, somewhere online and go like, okay, this is a Python to C++ translation thing, be my guest. But you're expected to use C and C++ in this class because 430 is the co-requisite, which means 400 has got to be the prerequisite. And 400 has a prerequisite of 360, which is plain C. I don't need your program to be object-oriented. Okay, it doesn't have to use a template class. It just has to work and compile, and it has to be your own code. Okay? Yep.
You said you're gonna give a little bit more details about like just a real quick one. Is what's being passed in just generic, like the letters? That's kind of what we're shooting. We're not necessarily worried about what's being passed in as far as the what we're going to be putting out in order. Like the A, will it always be an A, or will it be like a number or a name or something?
It would always be an A. So you're always using lowercase a to z. Each letter is representing a possible outcome.
Okay.
So that's going to be constant. We always start with A. So if I say, okay, you only got 2 possible outcomes, then it's between A and B. If I say it's 3 possible outcomes, it's between A, B, or C, and so on. Okay? All right. So the first thing we need to do, okay, in terms of representation and how you start with your coding, is you need to have a representation of what a set is. Okay, so we talked about the concept of a set from the very, very beginning of this entire semester, which is like, what, 9 weeks ago? But we never really talked about how to code it, how to do that in actual programming. Okay, so what do you guys think? How do we implement all those operations that we need to do? For instance, okay, for one thing that we need to do is to ask this question. Okay, I'm going to give you the prototype here. So I have to say is element of is going to be some kind of a function. Okay. If you want to use a char, because we use A all the way up to Z as individual outcomes as elements, that's fine. The other way to do it is, you can also use unsigned. In other words, you look at A as 0, B as 1, and so on. I would use that way, because it just makes more sense later on. You can always convert from A to Z all the way back to 0 to 25. How do you do that conversion? Right? Subtracting what? Yep, exactly. So it's very simple subtraction of the ASCII code of lowercase a can convert any lowercase letter back to 0 to 25 as a range of unsigned numbers. Okay, so I'm going to stay with 0 to 25 because it is just a lot easier to deal with, for many of the operations. So this is E, okay, which is a potential element. I don't know whether it is or not. And then we need some kind of a representation of a set. Okay, so I'm going to say this is a set. We call it X. And I want this subroutine to return a non-zero if and only if element E is in the set of X. So the question is, I'm only giving you the prototype. I don't even bother to tell you what set is. Okay, so now the question is, how would you represent a set in this case, where the elements are basically boiling down to 0 to 26. You can even have that as an assumption, as the only elements I need to be able to represent is going from 0 to 25, sorry. Yep.
Could you make like a structural code set?
You can make a structure, but I would say that even that is not needed. Yep. You can use an array, but an array of what? An array of unsigned, you can do that. It's quite wasteful, but yes, you can do it. because if you have an array of unsigned, okay, in a 64-bit, I'll get to that one. With a 64-bit processor, unsigned is probably by default 64-bit wide, okay. So you're basically using 26 times 64 bits to represent something that can be represented in just 26 bits. So your waste factor is 64 times. Yep.
Don't you just have to check if the number is 0 or greater or 25 or less than that, like in between 0 and 25?
But it is not necessarily a range. In other words, the set may contain element 0, element 5, element 10, and element 25. So it can be very sparse. So you have to be able to represent individual elements and not just ranges of elements. Okay. Okay, go ahead.
I was thinking like you have some kind of like 32-bit number. Each bit is associated with a
Yep.
index.
So that would be the most compact way to do it. Okay, it's also called a bitmap method, where each bit is mapping to a potential element that you want to represent. Question? Yeah.
I was thinking, are you going to use the Ewings?
That would be helpful because we can then specify exactly how wide of an integer we're dealing with. Yes. Any other questions? So using this particular method, I'll just kind of comment here and just say what we are doing here. I can say, now this is only my suggestion. You definitely do not have to do it this way. For those of you who are really good with C++, including all the template classes, you can use a set template class, okay, which means it is extremely wasteful in terms of the use of resources. So, okay, so this is a kind of like a sidetrack, kind of like a real important sidetrack here. So why do I care about efficiency, right? I mean, you have a i7 processors with how many cores now? Up to 8 cores, and each core has.
Well, if you can afford the i7 that has the 8 cores, most of them have 4 plus twice as many threads.
Yeah, 4 cores is plenty for a lot of applications. What about the amount of RAM that you have on the regular PC these days?
About 8 gigabytes.
8 gigabytes, 8 to 16, right? So if you have a slightly higher end, it may be 16, but if you have a professional gaming gig, you might have 32 gig, right? I mean, I'm pretty sure that 32 gig is possible now. I mean, it has to be. Yeah.
But you got to get a motherboard that has the most socket slots for it,
Yeah.
or be lucky and get a custom
Yeah.
one.
So why do we have to worry about wasting up to what 64 times 26 bytes, 64 times 26 bits, okay, which is not a whole lot of bytes. So why is that important?
Because you don't always have them.
Yep, exactly. Yep, go ahead.
Or making embedded systems.
I like that answer. Okay, for making embedded systems. So what we are talking about here are smaller controllers. The Arduino is basically one family of these MCUs. They have limited resources. It's not like they don't have resources, it's just not a whole lot. The MCU, or the microcontroller unit on those things, is called the AVR AT Mega 328. And as a chip, it has some resources, but not really a lot. Not the kind of resources that you're used to. So you can see right here, it has 2048 bytes of RAM, which is basically all the data space that you have. All the variables have to go into 2 kilobytes. When was the last time you measured resources of your programs in kilobytes instead of megabytes? Yep.
Never.
Yesterday.
Yesterday?
No.
So 2028 bytes for the entire RAM space. That includes the stack, all your global variables, and I strongly suggest that you do not use anything that will need a heap on something like this, because you won't have much of a heap to play with. Okay, so it has got 32 kilobytes of code space, which is actually plenty. I have done robotic applications using these controllers. Fully autonomous robot that can explore a maze. Remember the maze configuration and has the algorithm to optimize. It's the fastest way to go from one corner to the center of the maze. That boils down to about 32 kilobytes of code once compiled. The program is not written in assembly, it's written in regular C. Okay, so that means these controllers are not so simple that they're totally useless. They can still go into many applications to automate devices and whatnot. But that means you have to live with 2 kilobytes of RAM. So if you have to live with 2 kilobytes of RAM, that means you want to minimize the use of RAM as much as possible. And using only 1 bit to represent whether an element is present or absent is the way to do it. Is that okay? So do we understand why sometimes being kind of frugal with resources can actually be helpful? Not if you go work for Microsoft. Because you work for Microsoft, I'm almost for sure that your product supervisor will say, okay, you make assumptions based on the future PC in about a year and a half. Okay, so you can assume 32 gigs of RAM is the norm. You can assume octa-core is the norm. Write your code accordingly. I just need you to crank out the code as quickly as possible.
What the heck?
But that's how you end up with bloatware. That's how you end up with software that is using a lot more resources than it really should be using. Because they want to save development time, but they don't care about how hardware is utilized. I mean, that explains Windows
10.
Vista, right?
Oh, no. Wait, Wait, what
Windows
happened
8
with Windows
as well.
Vista? Did it die?
Windows 8
Windows 8
was a failure.
was bloated. Because Vista is more bloated.
8.1 was the fix, so 8.
Yeah. 8
Yeah,
was
well, they do that a lot. I mean, if you look at Windows 98, okay, that's before some of you were born, right?
Hey, whoa, a second. I had Windows 98.
So when they first came up with Windows 98, it was broken. And then they came up with Windows 98 SE, which stands for Windows 98 Second Edition. Second Edition fixed most of the problems, but they want people to buy it as an upgrade instead of saying, oops, this is, something on us, this is the fixed version of the operating
IBM
system.
did the same thing. IBM did the same thing.
IBM doesn't care about software licenses.
Oh.
They operate on completely different terms.
Okay.
Microsoft sells you licenses, which is basically you're buying a permission to use a program for possibly for a limited amount of time. IBM sells you contracts. Okay,
Oh.
you pay them X amount of money per month, and they'll take care of your problems.
Oh.
Okay, so in mafia terms, IBM is you're hiring the mafia to take care of a problem. You pay them, you say this is the problem, fix it. Okay? Microsoft is a weapon dealer. You buy your own weapon, you buy your own ammunition, DIY, okay? Do it yourself. And guess what? If you get hurt because the weapon is not fully functional, it's your fault.
Oh, wow. The arms dealer in the mafia.
If you use the weapon like a year after your license agreement, they'll come to your house and go, I'll give you a fine because you're using it beyond the terms that you agreed to.
Oh, wow.
Just use it offline.
They operate completely differently.
Okay.
Yeah. So IBM basically, and that's also why they retracted from the PC market, because that was not making money. It's actually draining their resources because of all the customer support and whatnot for the individual products. People who buy a laptop computer would call tech support and go like, okay, my PC is not working. Why is it not working? I cannot get the browser to work. I cannot sign in. How do I reset my password? La 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 la. They don't want to deal with that because they only want to deal with big corporations like Wells Fargo or state governments or federal governments, where people just go like, okay, this is what we want to set up. We want to set up a blah 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 server to do X, Y, and Z,
Right.
and here's a chunk of money. And IBM just go okay, we'll give you the solution. I'm not giving you the hardware. We're giving you the solution. So, completely different companies in terms of how they make money. Okay, so this is the reason why we want to be frugal. Okay. And there are always applications where these chips have a place. Yep, go ahead.
I was going to ask about the topic we were talking about before, like about the
Oh.
unsignings and bitmaps.
The 80 mega documentation?
No. About the function we were working on.
Okay, so we'll go back to the function.
Yeah, how this relates. So,
Okay.
I kind of didn't figure out how the bitmap thing works. So
Okay, so we'll talk about it now.
Okay.
Yep. So how many people know what a type def is in C? Okay, you define the type basically. Yep. So it's kind of the same thing as how you define a variable. So you basically say uint32_t is a set. Okay. Now obviously you have to do a pound include of stdint.h first, which stands for standard integer header file. And in it, it will first have a type def of uint32. uint32 basically just means unsigned integer 32-bit wide. Okay, there's another one that is 16-bit, another one that's 64-bit, but last time I checked, there's none for 128-bit yet. Okay, but this allows this code to be completely portable. In other words, this code, okay, this definition of what a set is going to work when you have GCC or G++ running on a 64-bit platform, on a 32-bit platform, or even on an 8-bit platform. Because that particular word uint32_t specifically says, I want an integer type that is unsigned and exactly 32-bit wide. So you don't have to worry about cross-platform compatibility when you use these terms. Instead of unsigned, unsigned long, or unsigned long long, this will take care of that problem. So I'm going to say here, so once you have a type def, you can use set as the name of a type now, okay? So now that's why we can use set as the name of a parameter, okay? So let's go ahead and take a look at an example, okay? So we'll say set, let's call it x, okay? So x is now a set. The question now is, how do I make x an empty set? Now each bit is representing the presence or the absence of a particular element in the set. And in this case, we actually have 6 spare elements because there are 32 bits, but we only need 26 of those. So we have some unused bits. We have 6 bits that are unused. Okay. So let me just write a comment here. Okay, so basically once you have a variable of the type set or uint32_t, bit 0 of x indicates the presence or absence of 0 as an element. Is that okay? And then bit I, okay, if I want to generalize, bit I of x as a variable indicates the presence or, okay, that's a typo up there, or absence of I as an element. Okay, so we can go all the way up to 31 because we count from 0. So we can have elements 0 all the way up to element 31, which is more than what we need for this homework assignment. Is that okay? So I'm hoping you guys are familiar with bitwise operations and also how integers are represented by individual bits. Okay, so how many of you are not comfortable with that view of an integer? That it is just a whole bunch of bits? Nope. Okay. All right. So we need a few functions. Okay, I'll give you the prototypes first. Another one is to add element to. Okay, so once again we specify what element are we adding, and this part depends on how you want to do it. If we do it in plain C, you will have to use a pointer because we are not changing what x is, we're changing what x is pointing to. Okay, but if you use C++, then you can use ampersand x, then you can change the parameter itself because you can pass by reference. Okay, I'm really hoping that everybody understood what I said. Okay, now it's your choice. Okay, if you want to do it in G++, then you just have to say pass by reference. If you want to do it in plain C, then you say it is a pointer to a set because you're changing what x is pointing to, because x itself is just a pointer. I'm just going to stick with plain C, because I don't use C++ much myself. Okay, so we'll go ahead and take a look at just these two first, okay, because these two form the most instructional basic code of this whole API or application programming interface. All right, so if I want to implement add element to, how would I do that? Okay, so this time I'm looking at the actual definition of this function. And how would I do that? In other words, I want bit E of whatever unsigned 32-bit integer that x is pointing to, I want that bit to be set. Yep.
So if you wanted like bit E, you take 2 to the power of E and then add it to x, and that would set that bit to 1.
But if you add, what if that bit is already set? So if you are adding, that won't work, because if you're adding to a bit that is already set, it will the carry will impact the other bits of that integer. So adding won't work, but you have some operation that is close to just adding, but it's not. It is a bitwise OR. Very good. Okay, so we can do a bitwise OR operation. So I'll just kind of throw in all the important stuff here first, and then we'll shuffle the box and see how we can arrange these things to make them work. Okay, so bitwise OR is important. What else? You mentioned power, which is good. Okay, so we understand the concept of how to get the bit, E in this case, of an integer. But power is a floating point library function, which I want to avoid. So the question is there an integer operation that can quickly let me specify whatever bit is corresponding to E? It's a shift operator. Okay, so we can do a left shift operator. So we'll throw that in as an ingredient. What else do you think is important? E is probably important, right? Okay, so we throw E into the whole mix. And then the X, or whatever X points to, is probably important too. So this is not E times X, it is E as one thing, and then whatever X is pointing to as the other thing. Okay, let me just be extra naggy and specify. We are looking at what X is pointing to, not just X itself. Okay, so we got all of these ingredients. There's one more, by the way. There's one more ingredient, which is 1, which is kind of useful. Okay? Okay. So how do you think we should combine these operators and values so that we can say, okay, since we're changing something, I would assume this can come in handy too. The assignment operator, right? Okay, so how do we combine all of this stuff here? This is a problem-solving, session, right? So then you have to think about each one, okay, and see in what context is it going to be useful. But before that, we have to kind of understand the operators themselves. What does it do? What does it need to get the job done? Okay, so let's look at the operators one by one and see if we know what they actually do. This is bitwise OR. What does it do? It ORs every bit. That is correct, but it's a little bit vague. Okay, so but I understand what you're talking about. Okay, so let's throw some more specific ways to specify terms in here. Okay, so what if you can say bit x of a bit I of something? Okay, you can designate a particular bit of a value. Then how do you define or how do you describe bitwise OR? Okay, so let's see if this works. Okay, we'll use R to designate the result. We'll use A to specify, a value. We'll specify B to specify the other value. Okay, so now I want to describe what is R equals to A bitwise or B. So how would you describe the result?
It's either
R.
A or B, or A and B. See them true or false?
No. Okay, so here's the thing. So we'll use the term that we already know for all. I mean this is stuff that we have talked about in this class already for all, right? Okay. So we say for all, and then I use I as an index in the set from 0 to, in this case, 32, 31, okay? And this is specifying an operation, or you can also look at this as an assertion, okay? So the assertion is after this assignment operation, the following is going to be true. So what do I say is true here? So I'm going to say, okay, I was tempted to use indexing, but I'm going to spell this out. So we'll say bit I of R equals to, okay, not single equal because I don't want to confuse assignment with comparison. It is it would be equaling to the bit I of A or bit I of B. There we go. Okay. In other words, what you're looking at as the last statement is a statement that is true, guaranteed to be true, after R equals to A bitwise or B. So does that describe what it does? Because one bit can either be a 0 or a 1. So that means this bit I or A or bit I or B of B can only be either a 0 or 1 as a result. That in return goes to bit I of R, which is your result variable. That's where you store it. Are we doing okay so far? Okay. So that's bitwise OR. What about the bit shift operation? How many people are not familiar with the bit shift operation? Okay. So the bit shift operation is, okay, so we'll use R equals a left shifted B many times, okay? So how would I describe the result here? R equals A times 2 to the power of B, okay. Okay, and put extra parentheses so that we know what this is. Okay. Is that okay? But it only has significance when you can look at how numbers are represented in binary. So is that part okay? Do we understand how to represent values in binary? Okay. Cool. All right. So given that we now know what is bitwise OR, which is basically just saying, okay, each bit position has its own OR operation, and we know what a bit shift is, which is basically inserting zeros on the right-hand side and shifting everything to the left-hand side. How do we combine these things so that we can implement what we want to do, which is adding an element to a particular set? Yep.
So you create a new set and then shift on that set, shift 1 E times, and then you take the order between that set and the original set and assign it to the original set?
Yep. Yep, you got it. So how do we shuffle these things to get it done? Good job. That's exactly it. So you got the right idea. So now it is a time to map your concept, your idea, to the syntax to specify what needs to be done. So it's time to, so you know what each component in the box is doing. You know what you want the entire box to do. So now it's time to shuffle the box and so that the things are arranged in the way that you want it to do. Now, there are several ways to do this. Okay, there's the faster way to do it, and then there's always the slower way to do it. If I tell you ahead of time that these are the 1, 2, 3, 4, 5, 6, so these are the 6 components that you need, and I'm not missing any components, I'm not giving you any extra components, how many ways can you shuffle these things where the order is important? We're getting back to combination versus permutation, right?
Okay.
So how many permutations do we get when we have to pick 6 items out of 6? That's your P function. It's 6 factorial, okay, which is 720 ways to do it. So you can explore all 720 ways and see which one works. That's the infinite number of monkey approach. If you get an infinite number of monkeys with an infinite number of time, then those monkeys can write anything that is conceivable. Shakespeare, to be specific here, yes, but they can also write anything, including trash novels and whatnot. Okay, but that would not be a very reasonable way to do it, because there are 720 possibilities, and many of those do not make sense at all. Okay, so we'll do it in a computer science way, okay? The way that you usually would do things, logically. So the question is, since I have I would start with the equal symbol, because it is an assignment operator, and that really locks down what can be on the left-hand side, at least, of the entire thing. What do you want to update? Okay, there are things that we cannot update here, okay? 1 is a constant. I cannot update 1. There's no way 1 is on the left-hand side of the equal symbol. These two are just operators. I cannot update an operator. They cannot be on the other side. Yes?
Are we using R, A, and B for,
Huh?
for the operations?
What?
No, are we using R, A, and B, or was that just an example?
That's just an example.
Okay.
That is a standalone example of RAB, but you're writing a subroutine up here. So now, okay, so what can be on the left-hand side of an equal operator has to be something that has what we call an L value, which means it is the address of something. There's an address of that thing. Okay, 1 has no address, is a constant. E has an address, but it's the address of a parameter. So do you want to change the parameter itself? Nope. Well, that leaves us with what x points to, right? Okay, this is a very redundant question, but I do want to emphasize it. Do you think what x points to has an address? And what would that address be? X. That's right. Okay. So now, okay, I'm just going to do this. I'm just going to shuffle things in the box. Okay. And we know that, you know, this is on the other side of the equality symbol, which means assignment. So cool. All right. So now we only have, you know, 4 things to consider on the right-hand side. Okay. It's one of those 4, you know. So with only 4 things, you know, now suddenly the monkey approach seems to make more sense, because 4 factorial is only what, 4 times 3 times 2 times 1, which is only 24. That's totally doable. Still doesn't make it the right way to do things. Generate and test has a place, but this is not one of those. Okay, so with this, okay, you mentioned a little bit earlier that you want to shift things by e number times, right? Okay, so that means we got this in the right place already. Okay, what do you want to shift by e many places? Exactly, that's the only value left, right? So now we say, okay, move this one over here. So that leaves an OR, and go like, where is that gonna go? What are we ORing? We are out of values to OR with on the right hand side. If I say that, you know, I gave you the right number of things to begin with, you cannot add anything else, where are you gonna put an OR? Before the equal sign, very good, because it's called a compound assignment operator, which means you're performing the operation, then the assignment. Okay, so we take this and put it here, and we're done. Cool. But do you see the process? You know, how we first come up with the ingredients. It's like, okay, what do we need to make this soup? Okay, you know, so you have to get all the ingredients. And then you look at each ingredient and go like, do I know what that means? What is this thing here? What is this thing here? And then you try to look at the operators, and then you use that as a clue of what needs to be here, what can only be there, and so on. So that locks down, you know, possibilities. And then whatever is left, okay, very few choices left, then you can just find out which one makes more sense. Is that okay? Are we okay with add element 2 at this point? Now obviously E can only go from 0 to 31, but assuming your program doesn't have any errors, that should not be an issue. If you want to add an assert, okay, to make sure that E does not exceed 31, go ahead, because you know that will throw an exception if it does exceed and cause your program to print a message before it dies. Yeah, just an if statement and a print or a CR or something like that, you know, would help. Okay, or you can just use the assert. Okay, do you guys know about the assert macro? Yes.
C assert.
Yeah. So C assert statement. So look it up, and you know it's not necessary. You don't have to do it, but it is recommended because it is a really useful way to make sure that your program, when your program is trying to do something that's unreasonable, you can catch it early on, so that you know you're not looking at like 20 lines down from where the problem was, because then you have to backtrace 10,000 lines to get back to the source of the problem. So the earlier you can basically make the program stop because something unreasonable has happened, the better. Okay? Alright, so I'm not going to put that here. And then we'll go back to the program and go like, okay, so if we know how to add an element to a particular set, how do I check whether an element is in a set or not? So now I'm going to implement this one. Unsigned E, set X, basically all the same stuff. So this time I'm returning a value. I'm returning something that is either a 0, which basically means element E is not in the set X, or it returns a non-zero value when E is actually in the set E. So how do we do this? Yep.
Can we do the same thing but with a logical AND operator?
With a bitwise AND. Yep, I got it. So we have the same thing. We have 1 shifted E many times. This is also called a bit mask. In other words, I have one 32-bit integer. If you look at it as a binary number, it's all zeros except for one position. That position is controlled by E. So in other words, you can say bit E of this integer is the only one within the 32 bits. Is that okay? It's called a bit mask because we're going to use it to quote-unquote mask everything else except for that one single bit position that we're interested in. Okay? And then you can use a bitwise AND. Okay? Bitwise AND, once again, is a AND operation that is applied on a per bit basis. Okay? So bit I of A is as a conjunction with bit I of B. The result, which is either 0 or 1, becomes bit I of the result of the bitwise AND operation. Is that okay? So we look at every single bit of the two sides of the bitwise AND operator, and then we say we take bit 0, and then do an AND operation. That becomes bit 0 of the result of the operator. Is that okay? All right, so now we just bitwise AND that with X. That's it. That's the whole thing. It does not return 0 or 1. It returns a 0 when the element is missing. It will return a potentially large number when the element is present. So you have to keep that in mind. It doesn't return 0 or 1. It is just 0 versus non-zero. But that's all we need to know because that's the convention of C and C++. Anything that is non-zero is considered as true. This is also why it's not going to work in Java. Has anyone tried to use that in Java? Like, if something is non-zero, it is the same thing as true, and use it in a Boolean context?
I've never gotten that far.
It does not work.
Okay, no, thank you.
Yeah. Okay, so we got these two. Let's see, what else do we need? We need something like this. Remove element from. Okay, so we're attempting to remove element E from set X. So once again, because we are changing X, we have to make sure that it is either passed by reference or passed by pointer. Pick one. Okay, so how would we do that? It's kind of the reverse of what we're doing here. So if it is the reverse of what we're doing here, I'm suspecting that I can kind of cheat a little bit here and start with that, right? Okay, so we are trying to turn a bit from 1 to 0, potentially 1. But we don't know whether it is a 1 already or whether it's already a 0. But we want to make sure that the result of that resulting bit at that position is a 0. That's what we want to do. Yep.
Add a 1 to E.
Hmm?
Add a 1 to E.
Why would that do anything?
Set it to 0. I mean, it will overrun.
No. So it depends on where you add the 1 to.
Oh, yeah, that
If you do add 1 to here, it's not going to work at all because you're just targeting a different bit. So that won't do a single thing, or what we want to do. If you do something like this, then you can potentially be setting another bit on top of the bit that you're already setting. Okay, so that's not going to do us any good. Okay, so what do we need to do? First of all, this is only good for turning something into a 1, right? Because if it's already a 1, it doesn't do a single thing. If it is not a 1 to begin with, if it's a 0 to begin with, then it can turn it into a 1. But it doesn't have any ability to turn something back into a 0. So what do you think can turn something back into a 0? Bitwise AND. Very good. Okay, so we now know that we need a bitwise AND operation. Let's see. In this case, yeah, that'll work, I think. Yeah, so bitwise AND is going to work. But then, what are you going to bitwise AND it with? Now, we know what we want to bitwise AND with has something to do with the bit mask of 1 shifted E many times, because that singles out a single bit that we are interested in. But if you just bitwise AND with that thing, it's going to 0 out everybody else and keep the bit that you want to turn into a 0 the same that it was. That doesn't seem like what we want to do. We want to negate that, okay? So we want a bitwise not, which is a tilde symbol, apply to this. So tilde is not the same thing as an exclamation point. Exclamation point is a logical not operator, which means it turns 0 into something that's non-zero. But which non-zero? We don't know. It's up to the compiler, up to the implementation. Bitwise not, on the other hand, is giving you a bitwise not operation, which means it will go through every single bit of whatever the expression is bitwise notting, and then for each bit of that value, it will turn it from a 0 to a 1, it will turn the 1 into a 0. It will flip the 0s and 1s for each bit position. Which means, in this case, it's going to flip every single one from a 0 into a 1, from a 0 into a 1, except for the one at bit E. It's going to go from a 1 back to a 0. In other words, you're looking at all 1s except for one position being a 0, and you're doing bitwise AND. So that position is going to be the only 1 bit position that will be cleared, that will turn into a 0. Is that okay? All right. Cool. Now, if you want to be careful, this is what I would also do, is I'm going to cast the 1 to the type of set, whatever set is, first. The reason you might need to do this is because if unsigned, okay, which is the type of E itself, is, and also 1, so I would do it over here as well. Because what is the type of 1 as a constant? And you don't specify. If you don't specify a typecast, you just say 1, in the context of some expression, what is the type of that integer? Everything has a type.
Boolean?
Nope, 1 is not a Boolean. There's no Boolean in C. It's an integer. It's an int. It's assigned integer, okay? But the width of an integer may or may not match what you want to do eventually with it. In other words, whatever x points to can be a different width compared to whatever 1 is. Now, if they are different, then you might have a problem. Because if 1 is is by default 16-bit, and whatever x points to is by default 32-bit wide, then you are using a 16-bit 1 and then do some shift operation. It will give you a 16-bit number. There's no way to affect or examine anything beyond bit 16. Is that okay? So that's why the casting is important, because that makes sure that whatever we are dealing with on the right-hand side of the operator has the same width as whatever we are trying to change on the left-hand side. It may not be needed, okay? But if you put it here, then your code becomes a lot more flexible in terms of cross-compiling. Is that okay? So now we know how to check whether an element is there or not. We know how to set an element. We know how to add an element to a set. We know how to remove an element from a set. Let's see what else we need to do. Occasionally, you might need to duplicate a set. In other words, you want to make a copy of a set. How do we do that? So we have set A and B. So how do we make a duplicate? How do we make A the same as B? Yep. This is supposed to be a really tricky question. That would copy B to A. You don't need any special function call because set is really just an integer. So regular assignment works just fine. Because you will need it. You will need to do something like this or pass it as a parameter by value. Okay, so let's see what else we need to do. How do you check whether a set is empty or not? Okay, so int is set empty, and this time we don't need to pass by reference because we can just pass by value in this case. So what are you going to return here? If I want to know whether x is an empty set or not, how do we do this? I think we need a big loop so that we can go through every single element, make sure that that element is absent, and then if all elements are absent, then we say, yep, it is empty. That will work, but we don't need to do it that way. How do we do it? Yep. Remember the double equal. Well, actually, in this case, the single equal would syntactically be correct, but then it will always return false. Right? If you forget this equal here, syntactically, it is okay. You're changing parameter x to an empty set, but then we'll always say that x is non-empty. So, don't you like C as a programming language? So this is the correct solution, okay? I don't want people to write down everything, including the incorrect answer, without commenting this is not the correct answer.
Next is compare, right?
Hmm?
Next is compare.
Sorry?
Is the next one comparing?
The next one is comparing.
Compare two sets. Two sets.
You probably don't need that for this assignment, okay? But comparing is easy. If you want to check whether two sets are the same or not, okay? How do you do that? Okay, int are sets the same, set x, set y. How do we know whether they are the same or not?
Return x.
Yep, there we go. Okay, so next one is going to be a tricky one because I know someone is going to say one thing, but it's actually the other one. Okay, is subset of. Okay, so we have set x and set y. You don't need this one for the homework assignment, but for the sake of understanding how to implement these things, it is kind of important. So how do we know whether x is a subset of y or not? Okay, so I'm going to show you guys the most common mistake here. That is not going to work. Now, it is not going to work in the sense that it doesn't catch all the cases. In some cases, it is sufficient, but not in all cases. Okay. In other words, x can be less than y as integers, but x is really not a subset of y. Yep.
I was making sure we're checking if x is a subset of y, not y subset of x, right?
We are asking whether x is a subset of y, but not proper, just subset of. So x and y can be the same and will still be returning true. Okay.
Do a loop for every element in x.
We can certainly do a loop. Yep. Mm-hmm.
Let's say do a bitwise or x and y, compare with y, and if they're equal, because if y contains x, you do a bitwise or, then you're going to get back y. And you compare y against that.
Okay, so you're basically using the definition of what subset of is basically if x is a subset of y, then every element in x is also going to be in y. If x is not a subset of y, then there are elements in x that are not in y. Okay, so the question is how do we identify whether that is the case or not? So I like that idea of using exclusive OR. We have x, we have y, and what else? What other ingredients do you think we need? Okay. So, okay. So let's try to think of it this way. We will try to do it not using the loop concept because that is really just wasteful. Okay. Okay. So we'll go with this one, and I think that would be the last thing that we'll talk about today. Okay. So if all elements of x, okay, let me rephrase it. if everything in X but not in Y is the same as X, then X is a subset of Y. Is that okay? If everything in X that is not in Y is an empty set. Okay, I take it back, sorry. Okay, if everything in X that is not in Y is an empty set, then X is a subset of Y. That makes sense. I think that's how we define subset of. Okay? Because this means everything in X is in fact in Y, and that's why it's called a subset. Okay, so now the question is, in terms of bitwise operations, how do we do this? How do we do a subtraction of two sets? How do we figure out whether there are things in X that are not in Y? Exclusive OR is one important thing, but it's not the only operator that we need. Okay, so we'll look at the implementation. Okay. X exclusive or Y, okay, is close to what we want, okay? This will basically be things that are in only one of the two sets, okay? So this will give us things that are only in X or only in Y, but not in both or neither. Is that okay? So that will tell us, not only the things that are in Y but not in X, but it will also tell us things that are in X but not in Y. But I need to single out and say, but I'm only interested in things that are originally in X. So what do you do with this? Okay, so you need an AND, but what are you ANDing it with?
Negation of Y.
With X. Because we're only interested in things that are originally in X. Are they also found, is it only in X, or it is always in X and in Y? Okay, so this will tell us things that are in X but not in Y. Okay, if this is telling us things that are in X but not in Y, don't you think it is equivalent to the set operation X minus Y? Then how do we compare that to an empty set? Yep, so we just say return X exclusive or Y, bitwise AND with X. Now I need to use extra parentheses because I cannot remember the priority of the operators. So using the extra parentheses, I can make sure that we do the exclusive OR first, which is basically saying, okay, we are only interested in things that are either in X or in Y, but not in both or not in neither. And then the bitwise AND operation is saying that, okay, let's not count the things that are only in Y because that's not of interest to me. I only want to know about the things that were originally in X. Are there things that are in X but not in Y? That's the question. If there's nothing that is in X but not in Y, then we know that X is a subset of Y. Is that making any sense? So what we want to do, when you come up with an expression like that, the first thing we want to do is to do a sanity check. Okay, so instead of actually writing the code and passing arguments to it, we just have to kind of run through this in our minds. So now the first question is, what if Y is an empty set? Because if X is non-empty and Y is empty, then this should always return false. Is that making any sense? So let's check out what's going to happen. So X is non-empty, Y is in fact empty. So what would that do? It would just be X, right? Anything exclusive OR with 0 is just the original thing. So the exclusive OR will give us X back. X and X is X, okay? And then X, which is non-zero, equals to 0 is false. Okay, cool. So if Y is an empty set, X is non-empty, it is always returning false because nothing other than the empty set itself can be a subset of an empty set, which kind of makes sense, Okay, so let's flip that and say, what if X is an empty set? Does that always return a non-zero? So this time we say X itself is empty. Y may be empty or non-empty. We don't really care. So if X is 0, then the exclusive OR becomes just Y itself, right? And remember, X is empty. And then you have a bitwise AND with an empty set, which is a 0. If you have an M-pers AND or an bitwise AND with 0, what is the result of that always? It's always a 0. 0 equals 0 is true. So that means if X is an empty set, it doesn't matter what Y is. This function always returns true. So it kind of passes the sanity check. Okay. What if X and Y are the same? In other words, we are looking at exactly the same set, which is always a subset of itself, right? So if X and Y are the same, what is this going to return? X and Y being the same means the exclusive OR is going to be a 0, because they will have the identical zeros lining up, identical ones lining up. So the exclusive OR is going to be a 0. 0 or whatever is a 0. 0 equals to 0 is true. So a set is always a subset of itself. So I haven't really tested the code yet, right? But I can go through all the extreme cases and go like, it makes sense in all the extreme cases. Okay, now would be a good time to actually test the with actual values that are non-empty. But if it doesn't pass one of these quote unquote sanity checks, then I don't even have to bother to check it with anything else. Cool. Okay, here's the other one. Intersection. You guys would like this one. You go like, yeah, but we are already over time. I need to go to another class. Can we do this in 2 seconds? Yes.
Isn't the return type supposed to be a set?
Yes. Very good. Thank you. Forgot about that. There we go. Yep, it's just a bitwise AND. What about union? Bitwise OR. Yep. You can see how the bitwise operation thing, using the bitmap mechanism to represent the set, certainly has a lot of advantages, because we can boil a lot of the set operations just down to integer bitwise operations, which are one, very efficient in terms of implementation, both time-wise and storage-wise. You'll be minimizing the use of RAM, but it will be fast to compute as well. Okay, so don't forget this stuff. Okay, because I'm gonna save the file just in case. We'll continue with this discussion on Wednesday, because on Wednesday I'll give you the actual assignment of the omega generator assignment. Omega generator, yes. Omega Supreme.
Omega.
Nope, wait, I need to turn off OBS, otherwise it will start